The first 3 minutes attempts to explain the early stages of the universe after the Big Bang. Early in the book, Weinberg explores the origins and implications of the Hubble constant and addresses the evidence collected for the expansion of the universe. He then tells the story behind the discovery of the cosmic microwave background. After giving the reader a basis of understanding of astrophysics and particle physics, Weinberg lays out the makeup of the universe after its origin in a series of frozen frames. According to our best understanding of the universe, about 13.8 billion years ago, the Big Bang took place. Then, a massive expansion occurred, which blew up a possible singularity like a balloon, eventually giving birth to our universe. The 3 minutes were followed up by many different epochs and versatile nucleosynthesis processes to create the universe we live in today. But, the first 3 minutes formed the period which gave us the most fundamental elements of our existence, that is, hydrogen and helium, and set up the stage for the advanced processes to occur. This undoubtedly makes the first 3 minutes after the Big Bang the most crucial minutes in the history of the evolution of our universe. So, here's what physicists think happened in the first 3 minutes after the Big Bang. We can divide these first 3 minutes into 7 crucial epochs or eras. Each epoch had a different temperature and density, and understanding the physics of each era. The Planck Epoch. Soon after the Big Bang, the first period that came into existence was the Planck Epoch. At this period, the universe's temperature was 10 to 32 Kelvin, so high that all the 4 fundamental forces, gravitational force, electromagnetic force, weak force, and the strong force, of nature existed together as one superforce. This era lasted for 10 to the minus 43 seconds. Since, at the Planck scale, the current physical theories cannot be applied to calculate what happened, very little is known about the physics of the Planck Epoch. The GUT era. The GUT, or the Grand Unified Theory, era began when the universe was just 10 to the minus 43 seconds old and continued till 10 to the minus 36 seconds after the Big Bang. After the Planck era, the fundamental force of gravity split apart from the other 3 fundamental forces of the Standard Model. So now, the electroweak force, the strong force, and the electromagnetic force were one in the GUT era. Moreover, by the end of this era, the temperature had fallen to 10 to 29 Kelvin from 10 to 32 Kelvin. The inflationary and electroweak epoch. The electroweak epoch was the third one to fall in place after the Big Bang. In this era, strong force got separated from the other 2 forces, thus leaving behind the weak and electromagnetic forces as a single force. Moreover, cosmic inflation started when the universe was just 10 to the minus 33 seconds. During inflation, the universe expanded exponentially and grew up from the size of a proton to a size equivalent to that of a fist. During inflation, the universe expanded at a rate faster than the speed of light. However, the exact physics of this extensively accelerated expansion is still not evident. Cosmic inflation ended very soon, and later, the universe started expanding normally. Now, the universe is 10 to the minus 32 seconds old, the temperature has fallen to 100 trillion 10 to 26 Kelvin, and most importantly, W and Z bosons have also been formed. The Quark Epoch. The electroweak epoch ended 10 to the minus 12 seconds after the Big Bang, and then began the Quark Epoch. By then, the universe had cooled enough for the Higgs field to have a positive value. This caused the electromagnetic force and the weak force to split away from each other. So now, all 4 fundamental forces have attained their identity. As a result, all the available particles can interact with the Higgs field and can gain mass. However, the temperature is still very high for the quarks to merge to form hadrons such as protons and neutrons. Thus, in the Standard Model of physics, quarks are one of the most elementary entities. The Hadron Era. Hadrons are a class of particles that are formed from 2 or more quarks. Soon after the Quark Epoch ended, the Hadron Era started, 1 microsecond after the Big Bang. By this time, the temperature had fallen to an extent to allow the quarks from the previous era to combine to form hadrons. Although a slight matter-antimatter asymmetry from the earlier phases resulted in an elimination of antihadrons, still a majority of hadron-antihadron pairs eliminated each other. So what mostly remained by the end of this period were only the light-stable hadrons, protons and neutrons. The Hadron Epoch ended 1 second after the Big Bang. The Lepton Epoch, when the universe became 1 second old, its temperature became favorable enough to form another class of elementary particles, the leptons. Leptons are a kind of fundamental particles in nature, and thus are not composed further of any constituent particles like hadrons. An electron is a classic example of a lepton. So now, by this time, leptons and antileptons started forming, and this production continued for 10 seconds. The leptons and antileptons remained in thermal equilibrium, as the energy of photons was still high enough to produce electron-positron pairs. However, the universe was still opaque as the photons could easily get scattered by these free electrons. The beginning of nucleosynthesis. By now, the universe contained protons, neutrons, electrons, and photons. The photons outnumbered the massive particles by billions to 1. Thus, all four fundamental forces had acquired their present-day form. Now, it was time for the most important process of nucleosynthesis to begin. In simple words, nucleosynthesis is when new atomic nuclei are formed from pre-existing nucleons and smaller nuclei. This is the process via which most of the heavier elements form in our universe. So now, at the age of 2 minutes, the universe's temperature dropped below 1.2 billion degrees Kelvin. At this temperature, the average photon energy was 1.8 into 10 to minus 14 joules, equivalent to the binding energy of deuterium nuclei. A deuterium nucleus consists of a proton and a neutron held together by the strong nuclear force. So, after 2 minutes of the Big Bang, deuterium got formed by the fusion of protons and neutrons. This had happened for the first time after the Big Bang that the universe contained nuclei more complicated than a single proton. Finally, after 3 minutes of the Big Bang, the temperature of the universe dropped below 1 billion degrees Kelvin. At this temperature, the average energy of the photons was 1.5 into 10 to minus 14 joules, which was equivalent to the binding energy of helium nuclei. So, at the age of 3 minutes, deuterium, protons, and neutrons combined via different possible processes to form helium nuclei. The 3 minutes were followed up by many different epochs and versatile nucleosynthesis processes to create the universe we live in today. But, the first 3 minutes formed the period which gave us the most fundamental elements of our existence, that is, hydrogen and helium, and set up the stage for the advanced processes to occur. This undoubtedly makes the first 3 minutes after the Big Bang the most crucial minutes in the history of the evolution of our universe. Thank you.